Alpha and 1 over alpha are the roots of the quadratic equation 3kx squared minus 18tx plus 2k plus 3 equals 0, where t and k are constants. Find the value of k. Now in the previous video I showed that the sum of the roots alpha and beta of any quadratic equation is given by minus b over a. The product of the roots of a quadratic equation is given by c over a, where a is the coefficient of x squared, b is the coefficient of x, and c is the constant term in a quadratic equation. Now, the roots of this quadratic equation are alpha and 1 over alpha. So let's look at the sum of the roots. Okay, I'm calling beta 1 over alpha. The sum of the roots is given by minus b over a. So we've minus b. What's b? B is the coefficient of x, which is minus 18t. That's a constant, because t is a constant. A is the coefficient of x squared, which is 3k. This simplifies down a bit to plus 6t over k. Now this isn't very helpful in finding k, so let's consider the product of the roots. So one root is alpha, the other root is 1 over alpha. So this is our beta, if you like. And we multiply them. But look, if we multiply these together, we get 1. And we know that that's equal to c over a, where c is the constant term. Now the constant term of this quadratic equation is 2k plus 3. And we divide by a, which is the coefficient of x squared, which is 3k. Now you see we have an equation with just one unknown in it, and we can solve it to find k. So we get 3k equals 2k plus 3. From this we get 1k equals 3, k equals 3. Now, we can rewrite our quadratic equation, replacing k with 3. So we'll have 3 times 3x squared, or 9x squared, minus 18tx. And we plug 3 in for k here, so we get 2 times 3 is 6 plus 3 is 9. If one of the roots is 4 times the other, find the possible values of t. One of the roots is alpha, so let's say it's 4 times the other root, 4 times 1 over alpha, which is 4 over alpha. Now it shouldn't matter which root we choose. I could have chosen 1 over alpha and said that it's 4 times the other root being alpha. So it shouldn't actually matter which way we choose to do this, because it doesn't say otherwise. From this we see that alpha squared equals 4, so alpha equals plus 2 or minus 2. Now we know from the first part that the sum of the roots, alpha plus 1 over alpha, is given by 6t over k, but we found that k was 3, so I can plug 3 in for k, so I get 6t divided by 3 is 2t. We know that alpha is plus or minus 2. Let's take alpha equals 2. So we plug 2 in here, we get 2 plus 1 over 2, that's 2.5. So we get 2.5 equals 2t. So t is 2.5 divided by 2. That's 1.25. If we take alpha equals minus 2 and plug it in, we get minus 2.5 equals 2t, or t equals minus 2.5 divided by 2, which is minus 1.25. So these are the two values of t. The equation x squared minus 12x plus 16 equals 0 has roots alpha squared and beta squared, where alpha and beta are both greater than 0. Find the value of alpha times beta. Now we know that the sum of the roots of a quadratic equation is given by minus b over a. So the roots of this quadratic equation are alpha squared and beta squared. So the sum is alpha squared plus beta squared. And that's given by minus b over a, where b is the coefficient of x and a is the coefficient of x squared. b is minus 12, a is 1. So we get minus 12 over 1, which is plus 12. Now we also know that the product of the roots of a quadratic equation is given by c over a, where c is the constant term and a is the coefficient of x squared. So the roots of this quadratic equation happen to be alpha squared and beta squared, so the product is alpha squared multiplied by beta squared. C for this equation is 16, a is 1, so we have 16 divided by 1, which is 16. Now, it's easy to get alpha beta because we know that alpha squared beta squared is 16. So alpha beta is just the square root of 16, which is plus or minus 4. The square root of alpha squared beta squared is alpha beta. The square root of 16 is plus or minus 4. Now we're given some extra information about alpha and beta. We're given that both alpha and beta are positive. And if we multiply two positive numbers together, we have to get a positive number. So that means we cannot have minus 4 here. So alpha beta is equal to plus 4. In part 2, we have to find the value of alpha plus beta. Now in the previous video, you saw this identity, which is easy to check. So we can use this identity to find alpha plus beta. We know that alpha squared plus beta squared is 12. And we know that alpha beta is 4. So we have minus 2 times 4, which is minus 8. So you can see that alpha plus beta squared is 12 plus 8, which is 20. So alpha plus beta must equal the square root of 20. And we're taking the positive square root of 20, not the negative square root, because alpha and beta are positive numbers. One of the roots of px squared plus qx plus r equals 0 is n times the other root. Express r in terms of p, q, and n. Let's say the roots are alpha and beta. That's usually what they're called. The sum of the roots is given by minus b over a. B for this quadratic equation is q. A is p. So we have minus q over p. The product of the roots, alpha beta, is given by c over a. C is r, a is p. We also know that one of the roots is n times the other. So you can pick any root you like, either alpha or beta, and set it equal to n times the other root. So I'm setting beta equals n times alpha. So I can write alpha plus beta as alpha plus n times alpha. I can factorize alpha out of this to get 1 plus n times alpha. And that's equal to minus q over p. I then multiply alpha by beta. Well, I'm multiplying alpha by n times alpha. Alpha times n times alpha is n alpha squared. And that's equal to r over p. Now we want to get r in terms of p, q, and n. So I have to eliminate alpha between these two equations. One way to do this would be to square both sides of this. That will introduce alpha squared. So this equation will have a similar form to this one. So if I square both sides of this, I get 1 plus n squared alpha squared equals this thing squared, which is q squared over p squared. Probably the quickest way to get rid of alpha is to divide this equation by this equation here. So I take the left hand side of this equation and divide by the left hand side of this equation. I take the right hand side of this equation and divide by the right hand side of this equation. So alpha squared disappears. So doing this division on the right hand side, we have q squared over p squared multiplied by p over r. And I can cancel one of the p's, so I end up with q squared over p times r. All we have to do now is isolate r. You could just cross multiply and do that, or what I did was to turn both sides upside down. I turned this fraction upside down to get this, and I turned this fraction upside down to get this here. Then you can multiply both sides by q squared and divide both sides by p, and you'll end up getting this. You want r in terms of p, q, and n. One of the roots of x squared plus qx plus r equals 0 is 5 times the other root. If q and r are positive integers, determine the set of possible values of q. Now we know that the situation in part 2 is the same as the situation in part 1, but with n equal to 5. So 5 takes the place of n. And p must equal 1. See, we've 1x squared here. So this equation has exactly the same form as this equation if we let p equal 1. And we're saying that one of the roots of this equation is 5 times the other. And one of the roots of this equation here from part 1 is n times the other. So we just set n equal to 5. So this relation will apply. We just replace n with 5 and p with 1. So we have 5q squared in the numerator. In the denominator we have 1 plus 5 is 6. 6 squared is 36. We have 36p in the denominator. Now we're interested in the set of possible values of q. Multiplying both sides by 36, we get 5q squared equals 36r. Then we divide both sides by 5 and take the square root. We get q equals root 36r over 5. Now we're given that both q and r are positive integers. That means that they are natural numbers. So that means that this expression in here must be a square. It must be the square of some integer, because then we can take the square root and get an integer. We want q to be a positive integer. So how do we ensure that this thing in here is a square? Well, the way you do that is let r equal 5k squared, where k is an integer. And of course r is going to be an integer automatically, because if k is an integer, then if we square it and multiply it by 5, we see that r is obviously an integer. So let's see why that is so. We just put 5k squared in for r. So this will break down to root 36 times k squared, which is 6k. You see, we choose 5k squared so that the 5's will cancel. And then we're left with 36k squared inside the square root. But 36k squared is a perfect square. Its square root is 6k. 6k is an integer, because k is an integer. So q has the form 6 times k, where k is an integer. Actually, we want q to be a positive integer, or a natural number. So, and for it to have this form here, well then q could equal 6 times 1, which is 6, or 6 times 2, which is 12, or 6 times 3, which is 18, and so on. Find a range of values of t an element of r for which the quadratic equation 2t minus 1x squared plus 5tx plus 2t equals 0 has real roots. Now we know that the roots of a quadratic equation are given by this formula here. For real roots, we want the discriminant, that's what's inside the square root sign, to be either positive or 0. If it's negative, we're getting the square root of a negative number, and then we're dealing with complex roots. The square root of a negative number is an imaginary quantity. So we calculate b squared minus 4ac for this quadratic equation. A is 2t minus 1. B, the coefficient of x, is 2t. The constant term is 2t in this quadratic equation. So b squared is 5t squared. Then we have minus 4 times a. A is 2t minus 1 times c is 2t, and we want that to be greater than or equal to 0 if we want real roots. So we can now determine what values t must have if we solve this quadratic inequality. So squaring this, we get 25t squared. If we multiply in here, we have 2t times 2t is 4t squared, by minus 4 is minus 16t squared. We get a minus 2t times minus 4, that's plus 8t. Gathering these up, we get 9t squared plus 8t is greater than or equal to 0. So this is a quadratic inequality. It's in standard form. We have 0 on the right hand side. The way we solve these is to first solve the equation 9t squared plus 8t equals 0. This is an easy quadratic equation to solve because we can just factorize t out of both of these terms. We don't have any constant term, so it's easy to get the factors. One of the factors is t, the other factor is 9t plus 8. Since the product is 0, we put each factor in turn equal to 0. So we put this factor equal to 0, giving t equals 0. When we put the other factor equal to 0, we get t equals minus 8 over 9. The next step is to look at a graph of this expression here. The graph of y equals 9t squared plus 8t. So t is the independent variable. It's our horizontal axis. Since this is a quadratic function, and since the t squared term is positive, we have an upright U-shape, and it crosses the t-axis at the two roots, at 0 and at minus 8/9. We are interested in the values of t for which y is greater than or equal to 0. So it's part of the graph for which the y values are greater than or equal to 0 is indicated here. So if you take this point here, the y value is greater than 0. Now we include these points. As for these points, y is equal to 0. So we can have y greater than or equal to 0. So the t values that correspond to that region are t greater than or equal to 0 and t less than or equal to minus 8/9. So this section here and this section here gives the solution of our quadratic inequality. These values of t will give us a quadratic equation which has real roots. In part 2 we have to explain why the roots are real when t is an integer. Well, let's look at integers. I've shown positive integers here, including 0. Well, you can see that all these values satisfy the condition that t is greater than or equal to 0. 0 is greater than or equal to 0, so is 1, so is 2, so is 3, etc. So you can see that all these values are part of our solution set. So if we take any positive integer, plug it in for t, we will have an equation that has real roots. And the situation is similar for negative integers. Minus 1 is included in this region here. Minus 1 is less than minus 8/9. Minus 1 is somewhere here, because minus 1 is actually minus 9/9. So minus 1 is less than minus 8/9. So is minus 2 and minus 3 and so on. So all these negative integers are part of our solution set that solves our quadratic inequality here. So integers are part of this solution set. That's the solution to part 1. The solution set in part 1 is t greater than or equal to 0 and t less than or equal to minus 8/9. Integers are really, well, a better word is to say integers are a subset of the solution set. So integers means both positive and negative integers, including 0.